What you're looking at is my step-by-step switching system demonstration unit. It has two shelves of step-by-step switches. On the bottom shelf, starting at the left, is the line finder, followed by the first and second selector. On the top shelf, starting at the left, is the third, fourth, and fifth selectors, and then finally the tall switch on the right is the connector. This video is going to be all about the connector. The connector is taller than the other switches because it has more relays, and it has more relays because it has more functions to perform. The connector processes the last two digits of the call, these being the tens and units digits of the called station number. In addition to the common step-by-step operations of vertical and rotary stepping, the connector has to perform a line busy test on the called station, ring the called station, trip the ring on call answer, provide answer supervision, and supervise the call connection. Let's take a quick look at a connector in operation. I'm going to scan up and down the connector to give you an idea of its component makeup while I comment on some pertinent aspects of connectors in general. There are three main categories of connectors. The first category concerns the call type, local or toll. Some connectors handle local calls only, some handle toll calls only, and others handle a combination of both local and toll calls. This particular connector is a combination local and toll connector. The second category is the type of ringing that a connector can provide. Some provide only one ring type, which is a long ring, and that is what this connector provides. Others provide two ring types, a short and a long, and yet others can provide 5 coded combinations of short and long rings to serve up to 10 stations sharing one line. And then there are harmonic ringing connectors that provide different ringing frequencies to telephone sets tuned to respond to a specific frequency. The third category is the hunting capability. There are connectors designed to serve businesses with more than one line. These connectors have the capability of hunting across all the lines of the business in order to complete a connection to an idle line, even though the telephone number connected to may be different than the one that is dialed. Other connectors, of course, don't have hunting capability, and the one you're looking at here does not. So this connector is a combination local and toll, non-hunting, one-ring connector. In this video, we are going to describe a local intra-office call to a single-party station. The toll components of the connector will be identified, but not described. This is a Bell Labs and Western Electric designed connector, but it was manufactured by Northern Electric in 1947. The switch is defined by its equipment drawing number, which is ED30228. So starting at the top of the connector and working our way down are the 10 relays, A, B, C, D, E, F, G, H, J, and K. We'll be discussing all of these relays in some detail except the J and the H relays, which are only used on toll calls and will not be covered in this video. The shaft spring provides the tension needed to make the shaft rotate anti-clockwise upon the disconnection of the call. The shaft spring bracket is the support base for the shaft spring. This bracket moves up and down with the vertical motion of the shaft, but it does not rotate with the shaft. The bottom of the spring is firmly attached to this bracket. The normal pin is fixed to the shaft, and so it moves up and down with the shaft and rotates with the shaft. It stops the anti-clockwise rotation of the shaft upon disconnection of the call, when it strikes the shaft spring bracket. It also rests on top of the off-normal finger when the shaft is in its normal position. This keeps the off-normal finger released until the shaft moves vertically off-normal. The normal pin clamp anchors the normal pin to the shaft. When the shaft first steps vertically off normal, The off-normal finger pivots upwards, which allows the vertical off-normal springs to operate. These contacts provide part of the operating path for the stepping magnets and the release magnet. This is the vertical ratchet. It is attached to the shaft and so moves up and down and rotates with the shaft. It provides the 10 teeth required for vertical stepping. Each tooth corresponds to one level in the bank assembly. The teeth are engaged by a vertical pawl that pushes the ratchet upwards by one step per engagement. Each step raises the shaft an amount equal to the distance between two bank levels. Just below the vertical ratchet is the rotary ratchet. It is also attached to the shaft and moves up and down and rotates with the shaft. It provides the teeth required for rotary stepping. Each tooth corresponds to one horizontal terminal position on any level of the bank assembly. The teeth are engaged by a rotary pawl that rotates the ratchet clockwise by one step per engagement. Each step rotates the shaft an amount equal to the distance between two bank terminals. This is the double dog, so called because it has two functional legs. The upper leg engages the vertical ratchet teeth to prevent the shaft from slipping down between pulses during vertical stepping. The lower leg engages the rotary ratchet teeth to prevent anti-clockwise rotation of the shaft between pulses during rotary stepping. After rotary stepping has finished, the lower leg also holds the shaft stationary in its off-normal position for the duration of the call. This is the stationary dog, so called because it doesn't move. The upper leg of the stationary dog is engaged by one of the vertical ratchet teeth during shaft rotation. As such, this leg supports the shaft during its clockwise rotation when rotary stepping and during its anti-clockwise rotation when releasing. It also supports the shaft in its stationary off-normal position for the duration of the call. The lower leg just provides a stop for the released position of the vertical pawl. Now let's continue down the shaft. At the bottom of the shaft are mounted the upper and the lower wiper assemblies. These wiper assemblies are attached to the shaft and so move up and down and rotate with the shaft. The purpose of the wipers is to sweep across bank terminals, as you see here. When the wipers come to rest on a set of bank terminals, as you see here, they provide electrical conductivity between the connector circuitry and the bank terminals. The wipers are connected to the connector switch circuitry by means of these flexible wiper cords. The lower wiper assembly provides the transmission path for the voice and other signals. The transmission path consists of two wires designated as the tip and the ring. The upper wiper is the ring wiper, and the lower wiper is the tip wiper. The upper wiper assembly provides a path for the switch control lead, which is called the sleeve lead. A line busy or idle status is received by the connector on this lead. In addition, the connector can transmit a called line busy indicator through the sleeve lead wiper. In the top wiper assembly, the bottom side wiper is the sleeve wiper. On this type of connector, the top side wiper is not used at all. Accordingly, the top side bank terminals on the upper tier of the bank assembly are also not utilized. Progressing down the right side of the connector, you can see the contact spring assemblies for each of the right-hand side relays. Of course, there's a similar set of contact assemblies on the left side. Notice, however, that the K relay is a little different in that it has two contact spring assemblies, a top set and a bottom set. This is the release armature. It operates at the end of each call to disengage the double dog from the ratchet teeth. This then allows the shaft to rotate anti-clockwise to its normal position. This is the release magnet. When energized, it operates the release armature. This is the double dog spring. It applies pressure on the double dog to force it to engage with the ratchet teeth. It sustains this pressure to keep the double dog engaged with the ratchet teeth until the appropriate release time at the end of the call. These are the test jacks where the CO technician can plug in and make a test call through the connector. Starting at the top, the jack spring connections are as follows. Top is incoming ring, second is incoming tip, third is incoming sleeve, and fourth is ground. The bottom 4 jacks are for toll testing purposes. If a coin is placed in between jack springs 3 and 4, it will ground the sleeve lead to the preceding circuits. This will make the connector appear busy so that it will not be selected while the technician is testing on it. This feature is also useful for tracing existing intra-office calls backwards from a called station to a calling station. Since the sleeve lead is permanently grounded by the coin, the switch train for this call will not release, even if the calling station hangs up. This is the right side vertical magnet. Its twin is adjacent to it on the left side. These magnets are energized and de-energized repeatedly during the pulsing of the tens digit to enable the vertical stepping function to occur. This is the vertical armature. It operates and releases repeatedly during the pulsing of the tens digit in concert with the energizing and de-energizing of the vertical magnets. This is the vertical pawl. It is attached to the end of an arm of the vertical armature. Each time the vertical armature operates, the pawl engages a vertical ratchet tooth and pushes the shaft upwards by 1 step. This is the head of the double dog. On top of the head is a tooth, over which the release link is latched. Whenever the release link is latched over the tooth, the double dog is prevented from engaging the ratchet teeth. It is unlatched on the first vertical step of the shaft by the operation of the vertical armature, and the double dog is freed up to rotate forward. These are the twin rotary magnets. These magnets are energized and de-energized repeatedly during the pulsing of the units digit to enable the rotary stepping function to occur. This is the rotary armature. It operates and releases repeatedly during the pulsing of the units digit in concert with the energizing and de-energizing of the rotary magnets. This is the rotary pawl, which is attached to the end of an arm on the rotary armature. Each time the rotary armature operates, the pawl engages a tooth in the rotary ratchet and rotates the shaft clockwise by 1 step. So here we're looking at a typical lineup of connector bays as they would appear in a number 1 step-by-step office. So these bays, they're 11.5 feet high, and they are capable of handling 7 shelves of connectors. So here we have a close-up of one of the connector shelves. And on a connector shelf, we have the capability of mounting 11 connectors. And on this particular shelf here, we have 9 that are mounted. We have 2 spare positions, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this one on the left side here is called a test connector. It is not used to process telephone calls from the public. This is used for access by plant maintenance forces in the telephone company and by switchboard operators trying to verify a particular line. So that one is not used. So we have then room for 10 connectors on that shelf, and this would be a standard shelf of what we would call regular connectors that would handle traffic to mostly residential customers or businesses with one line. So this would not handle the calls to businesses with several lines. We need a different kind of connector for that, called a rotary hunting connector or a level hunting connector, but we're not going to discuss those in this video. So regular connectors, 10 in a group. This is called a connector group. And as you can see, below the connectors are the connector banks. And the connector banks will have the 100 tip, ring, and sleeve outputs that will take them over to the distributing frame. Those 100 tip, ring, and sleeve outputs represent the last 2 digits of the telephone number. So this particular group represents 100 particular telephone numbers. So for example, if the telephone number Pennsylvania 65000 was part of this connector group, then this connector group would be serving the Pennsylvania 650XX number series. So that would be Pennsylvania 65000 to Pennsylvania 65099. So that's the 100 telephone numbers. Pennsylvania 65000 to Pennsylvania 65099. Here's a diagram of a selector bank, which is identical to a connector bank. So we'll use this diagram to explain the connector bank. There are 2 tiers. The upper tier contains the sleeve terminals and the lower tier contains the tip and ring terminals. The numbering scheme on the top tier identifies the last 2 digits, that is the tens and units digits, of the telephone number. There are 100 numbers ranging from 00 to 99. However, their arrangement is such that the tens digit corresponds to the bank level number and the units digit corresponds to the bank rotary position number. Rotary positions number 1 through 0 from left to right. For example, telephone number 11 is located on level 1, rotary position 1, while telephone number 00 is located on level 0, rotary position 0. The lower tier tip and ring numbering arrangement is identical to the upper tier. So there are 100 3-wire circuits cabled from the back of the connector bank to connecting blocks on the intermediate distributing frame. The wipers on the upper assembly access the sleeve terminals, while the wipers on the lower assembly access the tip and ring terminals. So the way the bank multipling works is that the 100 tip, ring, and sleeve leads on this bank are multiplied directly over to the 100 tip, ring, and sleeve terminals on this bank. And they are multiplied over to the 100 tip, ring, and sleeve terminals on this bank. And so on all the way across. And then finally the 100 tip, ring, and sleeve outputs are cabled into this terminal strip. And from the other side of the terminal strip, they're cabled over to the intermediate distributing frame. With the connector switch removed from the demonstration unit, we can now have a good look at the connector bank wiring. On this bank assembly, each circuit consists of 4 wires, one of which we are not using, so we will ignore it. The other 3 wires are the tip, ring, and sleeve. There are 100 sets of tip, ring, and sleeve leads cabled from this connector bank over to the intermediate distributing frame, where they terminate on telephone number connecting blocks. On the sides of the switch base are 2 pairs of bayonet-style mounting slots, an upper pair and a lower pair. What we're looking at here is the lower pair. On the connector mounting shelf there are 2 pairs of mounting pins, an upper pair and a lower pair. It is over these pins that the bayonet slots slide to mount the switch firmly into position. This is the connector plug. It has 24 prongs arranged in 12 sets of 2. The 2 prongs in each pair are separated by an insulator. The whole assembly is mounted to a wooden block which is fastened to the back of the switch base. When the switch is mounted onto the connector shelf, these 12 sets of prongs slide down in between 12 sets of jack springs with which they make electrical connectivity. Here are the 12 sets of jack springs that the plug prongs slide into. Nearly all the electrical connectivity between the connector and external circuits is handled through these jack springs. This includes DC power, ground, preceding circuit, ringing, and tone sources. The only exception is the connectivity to the called stations, which is handled by the wipers and bank assembly. This plug-and-play arrangement allows for easy removal and mounting of the connector switch. Here are some other components mounted on the rear side of the switch base. This double box assembly contains the capacitor network, which consists of 3 capacitors, the tip, ring, and A capacitors. The tip and ring capacitors are 2 microfarad voice transmission path capacitors that isolate the direct current top battery supplies from each other while allowing the passage of the alternating current voice signals. The A capacitor is a 0.04 microfarad capacitor that passes a small amount of the ringing current back to the calling party, which provides an audible ringing tone. The 183A network is a capacitor resistor network that prevents arcing on the A relay pulsing contacts. The 183B network is a capacitor resistor network that prevents arcing on the F relay ringing current contacts. Now, in a regular connector group, 10 connectors would nearly always be quite adequate to handle the load. So we have 10 connectors handling 100 telephone numbers, which is another way of saying that typically not more than 1 in 10 customers were using their telephones at any given time on an incoming call. So we have 10 connectors accessing 100 telephones. If all 10 connectors were in use and an 11th call came into or tried to get into that connector group, it would get blocked back at the 5th selector because there would be no idle connector path for it to get to, and it would return all trunks busy tone to the calling subscriber. But as I say, typically this was sufficient, and even here this is an office photo, so they only had 8 working connectors. The other 2 were blank because they didn't need them for the load. So here they can only have 8 simultaneous calls to those 100 telephone numbers. This is a diagram showing how the telephone set connects to the step-by-step equipment in the central office. The connector switch interacts with both the telephone set and the line circuit. So to fully describe the connector operation, it is necessary to have a good understanding of this diagram. A typical large step-by-step central office had 2 distributing frames, a main distributing frame, or MDF, and an intermediate distributing frame, or IDF. Each distributing frame has 2 sides. One is called the horizontal side, which I have designated with an H. The other is called the vertical side, which I have designated with a V. The sides are named based on the arrangement of their terminal strips, or connecting blocks, which are in horizontal rows on the H side and in vertical columns on the vertical side. The distributing frames don't contain any switching equipment. They are termination points for cables from central office equipment and from outside plant cable pairs. They provide an accessible place for flexible cable-to-cable interconnections to be made. Here's a photo of the MDF and the IDF in the central office. On the right-hand side is the MDF and on the left-hand side is the IDF. In both cases, we are only able to see the horizontal sides of these DFs with their multiple long horizontal rows of connecting blocks. Here's a small section of one vertical on the vertical side of the MDF. On the left, passing through the holes in the wooden fanning strips, are the incoming tip and ring cable pairs. Each wire goes through a high current protector called a heat coil, and each wire is also connected to a high voltage carbon cutout type of protector, which is partly contained inside these white porcelain blocks. The hidden far side is the output side, which looks similar to the input side and contains the cable pair tip and ring jumper connection terminals. Telephone sets are connected to a pair of wires called the tip and ring, which link into the central office via drop wires, distribution cables, and feeder cables. The feeder cables terminate on the vertical side of the MDF, so there is a physical 2-wire connection between the telephone set and the main distributing frame in the central office. The line circuit is part of the step-by-step switching equipment. It consists of two relays called the line relay and the cutoff relay. This circuit is utilized on every call, both originating from a station and incoming to a station. Every telephone line has a line circuit. However, not every station has its own line circuit. Some telephone lines serve more than one station. For example, there may be 2, 4, 8, or even 10 stations all sharing the same line circuit. The line circuits are 3-wire circuits consisting of the tip, ring, and sleeve wires that are cabled to the line finder banks and are also cabled to the vertical side of the intermediate distributing frame. In addition, the tip and ring wires of the line circuits are also cabled to the horizontal side of the MDF. The telephone number cables, which are 3 wires, tip, ring, and sleeve, are cabled from the connector banks to the horizontal side of the IDF. The cables terminate on terminal strips or connecting blocks, which have a cable side and a cross-connection side. The cross-connection side allows interconnections between any two cable terminations to be made by installing loosely placed jumpers on the distributing frame. This is a connecting block on my step-by-step demonstration unit. It is representative of what a typical step-by-step era connecting block on a distributing frame looked like. This is the cable connecting side, which terminates cables from central office equipment. Each wire is soldered to a terminal. The terminals extend right through the block and have similar solderable projections on the other side, which is the cross-connection side. Now we are looking at the cross-connection side, and here is a 3-wire jumper. So let's see how these cross connections are utilized to connect a telephone set to the step-by-step equipment. Let's assume we are establishing initial telephone service for a new customer. The customer is being provided with single-party flat-rate resident service. The telco installer will get a service order that will assign the telephone to a particular cable number and cable pair number. When installed, the set's tip and ring wires will be physically connected to a particular cable and pair termination on the vertical side of the main distributing frame. In the central office, the CO technician will also have a service order that indicates the particular line circuit, identified by the line finder group and terminal number, that the cable pair should be connected to. The tech installs a 2-wire jumper connecting the cable pair to the line circuit. This physically connects the telephone set tip and ring wires to a line circuit and to the line finder bank and terminal. The service order identifies the telephone number, so the tech also installs a 3-wire jumper connecting the telephone number on the horizontal side of the intermediate distributing frame to the same line circuit on the vertical side of the intermediate distributing frame. So now the telephone set's tip and ring wires are physically connected to a pair of connector bank terminals. The line circuit has 2 separate sleeve lead outputs. One goes to the vertical IDF termination, which has been cross-connected to the telephone number sleeve termination and thus through to the connector bank sleeve termination. The other sleeve lead is cabled directly to the line finder bank sleeve terminal. So let's take a look at the operation of the line relay and the cutoff relay in the line circuit. In the diagram, the dashed line represents a break contact of a relay. The path through the break contact is closed, that is, passable when the relay is released, and open, unpassable, when the relay is operated. The X indicates a make contact of a relay. The path through the make contact is open when the relay is released and closed when the relay is operated. The line relay is operated on originating calls only to initiate a dial tone request. It operates over the loop from the calling telephone set. The cutoff relay operates both on originating and incoming calls. On originating calls, the cutoff relay operates when the dial tone request has been successfully completed. This action opens its break contacts and releases the line relay. This stops it from continuing its request for a dial tone connection. It also makes the line appear busy to incoming calls by passing its originating connection sleeve ground through to the sleeve lead to the connector bank terminal. On incoming calls, the cutoff relay operates to prevent the line relay from operating when the incoming call is answered. This prevents a dial tone request from being initiated. There are 3 slow release relays in the connector. These are the B relay, the C relay, and the E relay. A slow release relay is designed to allow the relay to remain operated during short interruptions to its energizing current, or to delay its release to ensure that some other pertinent circuit event has had time to fully complete. The slow release feature is accomplished by the addition of a delaying device, which can be a copper slug mounted around the heel of the iron core, which is what the C relay uses, a solid metallic sleeve surrounding the iron core, which is what the B relay uses, or a secondary non-inductive shunt winding, which is what the E relay uses. The only visible delaying device that I have to show is the copper slug. Here you see a relay spool with its copper winding. On the heel end is a wide copper slug. This would provide the slow release feature. All 3 types of delaying devices work by using the principles of Lenz's law, in which the magnetic field induced in the delaying device opposes the collapsing magnetic field around the relay winding, and thereby slows this collapse. 2 other relays in the connector are slow operating relays. These are the F relay and the K relay. A slow operating relay is designed to not operate until some other pertinent circuit event has had adequate time to ensure its completion, or to prevent relay chatter during alternating current applications not meant to operate the relay, or to prevent operation from inadvertent momentary direct currents that are meant to be sustained in order to operate the relay. The delaying devices for both the F and the K relays are copper slugs mounted around the armature end of the iron core. These delaying devices also work using the principle of Lenz's law. When the relay winding is first energized, a magnetic field begins to build up. This induces a magnetic field around the delaying device that opposes and therefore delays this buildup. Now we are going to begin a detailed look at all the stages of the operation of the connector. The first stage is the idle stage. No relays are operated, and the shaft and wipers are in their normal rotary and vertical rest positions. We are going to follow the progress through the connector of a call through my demonstration unit to Pennsylvania 6 5000. We will begin at the immediately preceding 5th selector. This selector will process the dialing of the hundredths digit of the called station, which is a 0. As the dial returns, the 5th selector shaft steps vertically to the 10th level. It immediately begins rotary hunting for an idle connector. It finds an idle connector on the 10th set of bank terminals, and its wipers are brought to rest on these terminals. The 5th selector then extends the calling station's tip and ring leads through to the connector. At the connector, the A relay windings are bridged across the incoming tip and ring leads. The loop through the calling telephone set operates the A relay. The A relay controls the pulsing functions of the connector and also supplies the talk battery to the calling party. Make contacts of the A relay operate the B relay. The B relay is a slow release relay that remains operated for the duration of the call. It provides the holding ground to the incoming sleeve lead and also provides operating and holding grounds for various other relays in the connector. The caller dials the tens digit of the station number, which is a 0. During the dial's wind-up, the loop remains closed and the A and B relays remain operated. When the dial starts to return, the loop opens at the beginning of the first pulse. The opening of the loop releases the A relay. When the A relay releases, the B relay remains operated since it is a slow release relay. This combination provides an operating path for the C relay. The C relay is a slow release relay that monitors the incoming tens digit pulsing. At the end of tens digit pulsing, it releases, which transfers the switch operation from vertical to rotary stepping. In series with the C relay winding is the vertical magnet, so it becomes energized and the vertical armature operates. For clarity, I have added a clip here using my spare parts switch, showing the mechanical motions of the vertical pawl. It is the tip of the pawl that engages the ratchet teeth. When the vertical armature operates, the release link is pulled free from the double dog tooth. This allows the tension of the double dog spring to force the double dog legs to engage the ratchets. The double dog vertical leg engages the vertical ratchet teeth, and the double dog rotary leg engages the rotary ratchet teeth. The double dog legs remain engaged with the ratchet teeth until the switch is released. The double dog vertical leg prevents downward slipping of the shaft between pulses during vertical stepping. The double dog rotary leg prevents anti-clockwise rotation of the shaft between pulses during rotary stepping and maintains the off-normal rotary position of the shaft for the duration of the call after pulsing is finished. Attached to the end of the vertical armature is the vertical pawl. When the vertical armature operates, the pawl engages a tooth of the vertical ratchet and pushes it upwards one step. Since the shaft is attached to the vertical ratchet, it also moves upwards by one step, as does all apparatus attached to the shaft. This includes the normal pin and clamp assembly, which frees up the off-normal finger. For clarity, I have added a clip here using my spare part switch, showing the mechanical motions of the off-normal finger. The off-normal finger pivots upwards, allowing the tensioned vertical off-normal, or VON springs, to operate. These remain operated for the duration of the call and play a part in the energizing of the vertical and rotary magnets and the energizing and de-energizing of the release magnet. The wipers move vertically upwards by one step, which brings them in line with level 1 of the bank terminals. As the dial continues to return, it recloses the loop during the last part of the first pulse. The closed loop reoperates the A relay. This causes the vertical armature to release, and its attached vertical pawl to disengage from the vertical ratchet. As the dial continues to return, the second pulse begins and opens the loop. This releases the A relay, while the slow release B and C relays remain operated. This causes the vertical armature to reoperate, and its attached vertical pawl to re-engage the vertical ratchet. The pawl pushes the vertical ratchet up one step, along with the shaft and all of its attached apparatus. The wipers move vertically upwards by one more step, which brings them in line with level 2 of the bank terminals. As the dial continues to return, it recloses the loop during the last part of the second pulse. The closed loop reoperates the A relay. The vertical armature releases and its attached pawl disengages from the vertical ratchet. As the dial continues to return, for each remaining dial pulse of the tens digit, the A relay releases, the vertical armature and pawl operate, the shaft and its apparatus rise by one step, then the A relay operates and the vertical armature and pawl release. Now let's watch the actions of the connector as it processes the reception of the tens digit at normal speed. Remember that while the events are shown sequentially in the video, in actuality they occur simultaneously. At the end of the tens digit pulsing, the loop closes and the A relay reoperates. The vertical armature releases and its pawl disengages from the vertical ratchet. With the A relay remaining operated for an extended period, the holding path for the slow release C relay is opened for sufficient time to permit its release. It remains released for the duration of the call. Its release opens the energizing path for the vertical magnet and partially closes the operating path for the rotary magnet. At this point in time, only the A and B relays are operated and no further activity occurs in the connector during the interdigital interval. The caller now dials the units digit of the station number, which is also a 0. During the dial's wind-up, the loop remains closed and the A and B relays remain operated. When the dial starts to return, the loop opens at the beginning of the first pulse. This releases the A relay. With only the B relay and the VON springs operated, the path for operating the E relay is now closed. The E relay monitors the units digit pulses, and when pulsing is finished, it transfers the switch operation from rotary stepping to the ringing stage. It is a slow release relay and remains operated throughout the units digit pulsing and permits time for a called line busy test to be performed. The energizing path for the rotary magnets is closed at the same time as the operating path for the E relay. As a result, the rotary armature now operates. The rotary pawl is attached to the end of an arm of the rotary armature. When the rotary armature operates, its pawl engages a tooth on the rotary ratchet, which forces the ratchet to rotate clockwise one step. Of course, the shaft and all of its attached apparatus also rotate one step. For clarity, I have added a clip here using my spare parts switch, showing the mechanical motions of the rotary pawl. It is the tip of the pawl that engages the ratchet teeth. The rotation of the wipers by one step brings them to rest on the first terminal of the 10th bank level. As the dial continues to return, it recloses the loop during the last part of the first pulse. The closed loop reoperates the A relay. This releases the rotary armature, and its attached pawl disengages from the rotary ratchet. As the dial continues to return, for each remaining dial pulse of the units digit, the A relay releases, the rotary armature and its pawl operate, the shaft and its attached apparatus rotate by one step, then the A relay operates and the rotary armature and its pawl release. Now let's watch the actions of the connector as it processes the reception of the units digit at normal speed. Remember that while the events are shown sequentially in the video, in actuality they occur simultaneously. I should mention that when the tip and ring wipers sweep across the bank terminals, they are electrically dead. This prevents any noise interference from occurring when these wipers contact any terminals being used by other callers. At this point in time, the ring wiper, the tip wiper, and the sleeve wiper are all resting on terminal 00 of the bank assembly. So at this point in the progression of the call, the connector's tip ring and sleeve wipers are physically connected to the called station's line circuit, and the tip and ring wipers are physically connected to the called station's telephone set. Let's see how the shaft spring creates the tension required to rotate the shaft anti-clockwise to its rotary normal position when the connector releases at the end of the call. The top of the shaft spring is attached to the cap, which is fixed to the shaft. When the shaft rotates, the cap and the top of the spring rotate with it. The bottom of the spring is attached to the shaft spring bracket, which cannot rotate as it is fitted over the stationary normal post. The bottom of the spring cannot rotate, while the top of the spring can. So when the shaft rotates, the spring winds up, creating tension. As the last of the unit's digit pulses finishes, the loop through the telephone set closes and the A relay reoperates. This releases the rotary armature, and its attached pawl disengages from the rotary ratchet. The operation of the A relay also de-energizes the windings of the E relay, and after its slow release interval has lapsed, it releases. Before the E relay is able to release, the connector performs a busy test on the called station to see if the line is idle or is in use on another call. This test is performed by the G relay. One side of the G relay winding is permanently connected to negative 48 volt battery, and at this point in the call progression, the other side of the winding is connected through the sleeve wiper to the called station sleeve lead. If the called station is already in use on an originating call, there will be ground on the sleeve lead of its line circuit, originating from the switch train of that call. That sleeve lead is connected to the connector sleeve bank terminal by way of the jumper on the IDF. This ground will cause the G relay to operate. If the called station is already in use on an incoming call, one of the other connectors in this same connector group will be serving that call, and that connector would be supplying ground to the sleeve terminal of the called station. Because of the bank multiple, that ground will appear on the bank sleeve terminal of this connector, which will feed through to the G relay winding and cause the G relay to operate. In my demonstration unit, I am using a Lorraine Model F1 tone generator for both busy tone and dial tone. This model outputs a 600 cycles per second tone, which is amplitude modulated by a 120 cycles per second signal, and it sounds like this. This is fondly known as the Old City dial tone that was prevalent prior to the introduction of touch-tone telephone sets. To produce busy tone, the dial tone is simply fed through a device that interrupts the signal at a rate of 60 IPM, or interruptions per minute. The resulting tone sounds like this. So in the case of a busy line with the G relay operated, a make contact of this relay will pass busy tone to the incoming ring lead and back to the calling station. This action is taken because, well, back in the day, voicemail hadn't been invented. If the called line is idle, the sleeve lead will not be grounded and the G relay will not operate. Instead, when the slow release E relay releases, one side of the primary winding of the K relay will be connected to the sleeve wiper, and the other side of the winding will be connected to ground. The called station's sleeve terminal is connected through the IDF jumper to the called station's line circuit. In particular, it is connected to one side of the cutoff relay winding, The other side of the CO relay winding is connected to the negative 48-volt battery. This completes an operating path that operates both the CO relay in the line circuit and the K relay in the connector. Well, sort of. The K relay only partially operates. What does that mean? Let's take a look. When the K relay first operates, you'll notice that only contacts 1 and 2 make in the bottom set of contact springs. The remaining springs don't move, so it's only a partial operation. Notice that many of the contact springs are ganged together by these bushings. You can see the visual effect of this ganging as I manually operate and release the armature several times. Contacts 1 and 2 bottom are easily made before the combined tension of the ganged contact springs is encountered. The weak magnetic field produced by the K relay's primary winding is sufficient to operate the armature successfully against the tension of bottom contact springs 1 and 2, but not sufficient to successfully oppose the tensions of the ganged springs. For this, a much stronger magnetic field is required, and that is what is provided by the secondary winding. It has more than twice as many turns as the primary winding and receives a slightly higher operating current. With contacts 1 and 2 bottom operated, the energizing path for the secondary winding is closed and the K relay fully operates. It is important that the line circuit cutoff relay operates before the K relay fully operates. This is necessary to cut off the line relay from the tip and ring leads. As soon as the K relay fully operates, ringing current is sent over the tip and ring leads to the called station. It would also be sent to the line circuit if the cutoff relay wasn't operated, causing the line relay to chatter and initiate false dial tone requests. Also, if the called station picks up the handset at this point in time, the operated cutoff relay prevents the line relay from operating and initiating a dial tone request, since the called station is now committed to an incoming call. The fully operated K relay closes the path between the ringing generator and the tip and ring leads of the called station, which allows ringing of the called telephone to begin. It also puts direct ground on the called station sleeve lead, which maintains the operated condition of the cutoff relay in its line circuit until the call ends. In addition, this sleeve ground extends to all connector banks in the connector group, which makes the called station appear busy to any other connectors attempting to access it. Before we get into the ringing process, let's take a quick look at what would happen on a call to an unassigned telephone number. If the called number is not in service, there will be no IDF cross connection to a line circuit. If the IDF tip ring and sleeve terminals are just left unconnected, the sleeve bank terminal would be electrically dead, since there would be neither battery nor ground provided from a line circuit. So the G relay would not operate from busy line ground, and the K relay would not operate from idle line battery. The connector would stabilize with just its A and B relays operated, and no further connector action would occur. The calling station would hear only silence, a condition known as no ring, which was considered to be unacceptable by the Bell system. To ensure that no call ended up in a no ring condition, a process called intercept was provided. The IDF tip ring and sleeve terminations for all non-working telephone numbers were cross-connected to special intercept trunks, which provided a pathway either to a live operator or more commonly to a recorded announcement system that sounded typically like this.
The number you have reached is not in service. Please check the number and dial again.
Now let's start taking a look at the ringing functions on a call to an in-service number. In my step-by-step demo unit, ringing current is supplied by a Tel Labs Model 8102 ringing generator. It outputs a continuous 20 Hz alternating current at 105 volts. A 6-second ringing cycle, having a cadence of 2 seconds of ringing followed by 4 seconds of silence, is provided by a pylon ringing interrupter. This emulates the standard one-ring arrangement that would be provided to this type of connector in the central office. The alternating ringing current is superimposed over a 48-volt direct current supplied by my Valcom 48-volt DC power supply. The DC component is necessary to trip the ringing upon call answered. So now let's listen to the ringing at the called station. A small portion of the ringing current is passed through a 0.04 microfarad capacitor onto the incoming ring lead. This current passes through the calling telephone, where it generates an audible tone through the receiver. This tone provides an indication to the calling station that the called station is ringing. It sounds like this. The current from the ringing generator passes through the 200 ohm primary winding of the non-operated F relay. It flows through the tip and ring wipers onto the bank terminals and out to the telephone set. At this point, the only path through the telephone set is through the ringer capacitor and the ringer coils. The handset is resting on the switch hooks, and so there is no loop through the telephone set. So only the AC component of the ringing current is flowing. The DC component is blocked by the capacitor. The F relay is slow operating, and so the AC current flowing through its primary winding does not cause the relay to chatter. When the call is answered, the ringing is tripped immediately. Let's watch. The call is answered at the called station by lifting up the handset. The switch hooks pop up and close a loop through the telephone set. This loop allows the DC component of the ringing current to flow. The F relay primary winding is used to detect call answer. When the DC current flows through it, the relay partially operates in a fashion similar to the K relay. The weak magnetic field of the primary winding is not sufficient to overcome the combined tensions of the ganged contact springs, so only contacts 1 and 2 operate. Operated contacts 1 and 2 complete the energizing path for the F relay's secondary winding. The stronger magnetic field of the secondary winding causes the relay to fully operate. The operated F relay cuts off the ringing generator from the tip and ring leads, or in telephony terminology, trips the ring. It also bridges together the voice transmission paths of the calling and called stations. With the F relay fully operated, the called station tip and ring leads are now extended through to the D relay windings. Ground through the D relay secondary winding is connected to the ring wiper, and battery through the D relay primary winding is connected to the tip wiper. This constitutes the talk battery supply for the called station. The D relay now operates over the loop through the called telephone set. The operation of the D relay reverses the A relay battery and ground connections to the incoming tip and ring leads. Ground through the A relay primary winding is switched from tip to ring. Battery through the A relay secondary winding is switched from ring to tip. This changeover is known as answer supervision and is a method of informing preceding circuit charging equipment that the call has been answered and can be charged. This was used by such items as message rate trunks, coin control trunks, and long-distance charging equipment. The two direct current talk battery supplies provide power to the transmitter circuits of the telephone sets. The two microfarad capacitors on the tip and ring wires between the A and D battery supplies isolate each of the direct currents so they do not interfere with each other or affect the independent operate and release activities of the A and D relays. While the direct currents are blocked, the capacitors easily pass the alternating current voice signals produced by the inductors in the telephone sets. The connector is now in the connected stage with the calling and call stations able to converse. The connector remains stable in the connected stage with the A, B, D, F, and K relays remaining operated until the end of the call. When the calling station hangs up at the end of the call, the release sequence begins. With the handset back in its cradle, the loop through the telephone set is opened, and so the A relay releases. This releases the B relay. B released removes ground from the incoming sleeve lead, which causes the entire preceding switch train to release. B released also releases F, K, and D. The release of the K relay removes ground from the sleeve wiper. This removes the busy indicator for the called station from the sleeve terminal of the connector banks and releases the station's CO relay in its line circuit. At this point, the energizing path for the release magnet is closed and its armature operates. The pin on the bottom of the release armature pushes against the head of the double dog, which causes the legs of the double dog to disengage from the ratchets. And it allows the release link to re-latch over the tooth of the double dog head. With the leg of the double dog released from the rotary ratchet teeth, the tension of the wound-up shaft spring causes the shaft and all of its attached apparatus to rotate anti-clockwise until it is stopped by the normal pin striking the shaft spring bracket. The upper leg of the stationary dog is still engaged with the tooth of the vertical ratchet. As such, it provides support for the shaft as it rotates anti-clockwise. When the shaft reaches its normal rotary position, the stationary dog's upper leg rests inside the channel of the vertical ratchet, thus removing all support for the shaft. Without support, the shaft drops down to its normal position by force of gravity. This includes all of its attached apparatus, such as the wipers. As the shaft drops down, its normal pin will strike the off-normal finger. This causes the off-normal finger to pivot downwards, releasing the vertical off-normal springs. The released VON springs open the energizing path for the release magnet, and so its armature releases. At this point in time, all relays are released, all magnets are de-energized, and the shaft and all of its attached apparatus are in their normal rest position. The switch is once again in its idle stage. Okay, so let's go back now to the connected stage once again, and we're just approaching the end of a telephone call, but this time the calling station remains off hook, and only the called station hangs up. In the connector, only the D relay releases because its loop through the called telephone set is open. So other than the D relay, the switch remains in its connected stage and is under control of the calling station. So now let's see what happens when the called station attempts to originate a new call. The call begins by lifting the handset out of the cradle. At the called station's line circuit, the line relay should operate over the loop through the telephone set. However, the cutoff relay is still held operated by the connector. Break contacts of the cutoff relay keep the operating path for the line relay open, and so it cannot operate, and a dial tone request cannot be initiated. The call station cannot place a new call until the calling station hangs up and releases the connector. This condition was known as calling party hold, and it generated an audible and visual alarm in the central office, in response to which the CO technician was expected to go and manually release the connector switch to free up the called station. In later years, an option became available that provided an automatic timed release on calling party holds. However, this was long after my 1947 switch was built. If you're the called party in a step office and you don't hang up after the calling party has, you'll get dial tone. Here's why. So here's the calling station hanging up, and here's the called station remaining off hook. Since the calling station is hung up, the connector releases and ground is removed from the sleeve lead of the connector bank, which causes the cutoff relay of the called station to release. With the calling station off hook and the cutoff relay released, the path for operating the line relay is closed, and so the line relay operates. This initiates a dial tone request. A line finder is selected, which proceeds to find the called station's line. It connects it through to a first selector, which sends dial tone to the called station. Well, that completes my description of the step-by-step connector switch. However, there is one other related topic that I wanted to talk about. So the connector that we've just been describing can be used to provide selective ringing to two-party services. And here's a diagram showing how it's done. It's actually not a function of the connector itself, but is a function of the way we put the jumpers in on the intermediate distributing frame and the way in which the telephone sets are wired out at the customer's premises. So let's examine this example. We have a two-party line. Pennsylvania 62511 is the tip party set. Pennsylvania 65000 is the ring party set. So first of all, we'll call Pennsylvania 65000. So the ringing generator will send the ringing current out on the ring side, as it always does. The ringing goes out through the DFs, through the cable pair, and into the ring party telephone set. And in the ring party phone set, we have wired the ringers between the ring side of the line and ground. So the ringing current comes in, goes through the ringer's capacitor, through the ringer coils, to ground and back to the CO. So this telephone set rings. Now let's look at the tip party telephone set. While there is a path for the ringing current into the set, no current flows because the ring wire path is open at the set switch hook contacts. So this set will ring, this one will not. Now we're going to call the tip party set. So with the tip party set, the ringing current again will go out on the ring side of the line, but we have reversed the tip and ring jumpers at the intermediate distributing frame. So the ringing current goes out on the ring, but it's connected to the tip side at the line circuit, goes out across the distributing frames, out on the cable pair, and out to the tip party telephone set. And in the tip party telephone set, we have wired the ringer circuit from the tip wire to ground. So the ringing current goes through its capacitor, through the ringer coils, to ground and back to the central office. So this telephone will ring. This phone will not ring because while there is a path for the ringing current into the set, no current flows because the tip wire path is open at the set's switch hook contacts. So this Pennsylvania 62511 will ring, but Pennsylvania 65000 will not. And that's how we are able to provide selective ringing to two-party lines in the central office using standard one-ring connectors. This completes my video of the connector switch. I hope you have both enjoyed it and found it educational. If you have any questions, please put them in the comments section of the YouTube video, and I will attempt to answer them. Thanks for watching.